Okay, so yesterday we started talking about pointers. Actually, yesterday kind of did a review of pointers because you know the pointers from 102, CSE 102. I introduced two new keywords, new and delete. Okay, new is for malloc, delete is for free, and we don't use malloc and free anymore, or any of the standard C memory allocation, dynamic memory allocation functions because they are type independent, because they don't care about the type. So all they know is that you need to give them a number of bytes to allocate, and they give you the area with a pointer, and that's it. That was the whole functionality of malloc, calloc, etc. With the keyword, new operator, new. Okay, new knows about the types. When you say new int, it doesn't return a void pointer. It returns a integer pointer, and it definitely calls the constructor of this type. It calls the constructor of int, which does nothing actually. It doesn't do any initialization. Okay, or when you call new with an array, when you say give me a money array of size k, for example, it calls it makes k number of money objects, and it calls the constructor appropriate no parameter constructor for each of them. Okay, so new is much more than just memory allocation. It knows about the types. It returns a type pointer, and you don't need to typecast it to anything. Okay, it is already a correct type, and you are not supposed to mix the types with each other. You are supposed to use it like this. If you are getting a new integer, then you should use an integer pointer, not money pointer or void pointer, etc. Okay, what did we say at the beginning of the semester? C++ tries to be a strongly typed language. Okay, and that's the reflection of it in terms of memory allocation with two new keywords, new and delete. Okay, last time we talked about this. We said that what happens if there is no memory when the operator new works. Okay, then we checked against this null pointer. It's going to return us a null pointer, and if we have a null pointer, then we will say that we don't have enough memory. Well, actually, by allocating a single integer, which is 4 bytes, if you don't have that kind of memory, I mean 4 bytes out of gigabytes of memory on your computer, then you are in trouble anyway. Okay, because with the 4 bytes you won't be able to continue. Remember what I said? Okay, this is stack area which grows upwards. This is the heap area, grows downwards. Okay, I mean if you have only 4 bytes available or less than 4 bytes available in this free area, you won't be able to make any function calls, because that means that you don't have any space for your stack area either. So you are in trouble. But maybe this kind of a statement might be the possible use of this comparing against the null pointer. I am trying to get 1 million money objects. Okay, or is it 10 million? Yeah, 1 million. So it's a lot of memory. So you don't have that kind of memory. You need to be careful. You need to check if this MP same as null pointer. Okay, what is the type of null pointer? What is the type of null pointer?
Is it void pointer?
What?
Is it void pointer?
No. Well, it's kind of no void pointer, but you may think null pointer as but by the way, this null pointer is not like, remember when we do this, cout std, or well, okay, end of line. This end of line is defined inside the IO stream header. It is not part of the language. Cout is not part of the language. End of line is not part of the language. But null PTR is part of the language. It's a C++ keyword. Null, remember our null define. Null is not part of the language, right? It is defined somewhere. It's a define. Somebody defined null as 0. Okay, null pointer is part of the language. When you do this kind of a comparison, it's not a void pointer, but it's a money pointer with a value of 0. Okay, address of 0. So you may think null pointer as a pointer for each type, but its value is fixed, is constant, and its value is 0. So it is safe to, I mean, if you are thinking about, well, this is a money pointer, this is a void pointer, how come we are comparing these two? Okay, now I mean grammatically you are not comparing with a void pointer, you are comparing it with a money pointer. It's like this. Remember, what is the type of this pointer? It's a pointer to the current object. So it is, if I'm using it inside the money class, it's a money pointer. If I'm using it in a bank account class, it's a bank account pointer. Whatever you are using, okay? So this again is a special, it's a C++ keyword, is part of the language. Null pointer is something like that too. So we talked about this, and by the way, this is for older compilers. For older compilers, you check against the null pointer. For the newer compilers, or depending on your switches, okay, compiler switches, you get this behavior. For the newer compilers, we have another way of handling this new success, and we will talk about it when we come to the discussion of exceptions in a few weeks. Okay, so for the new compilers, okay, new operation fails, okay, the program terminates automatically, but there is a way to catch that exception, not to terminate and then take suitable action. We will look at this. Okay, we talked about this already. Okay, free storage is typically large. Okay, most of your programs won't use the whole memory at all. By the way, our operating systems, modern operating systems, whether it is Windows or Linux or some other kind of operating system, they are very robust in terms of memory usage. Okay, they are very robust in terms of memory usage. I have only 8 gigabytes of main memory on this computer, but I think I showed you how many programs I am running right now. I am literally running around 100 processes, and each one is capable of using more than a few gigabytes of memory. So if you add them up, you need more than 100 gigabytes of memory. Okay, I don't have it. Nobody has more than. Only a few people have more than 100 gigabytes of memory. So how do we fit all that kind of memory requirement inside 8 gigabytes of memory? Operating systems are smart. They don't keep all the programs in the memory. They keep parts of them, not all of them, but parts of them in the memory. The rest stays on the disk. Okay, so they swap back and forth. Okay, they swap back and forth. So if a program needs more memory, okay, it doesn't say no. Okay, I'm going to give you the memory, and it will maybe write some of the running programs to the disk, so memory is available, or write some part of the other programs or my program to the disk because the memory is available. So usually you don't think this is a fixed size. Okay, you don't think that this is a fixed size. You don't say, okay, I have 2 gigabytes of memory available for my program and I'm going to use it. No. At the beginning, if this area is huge, if you have a small code, small stack and small heap, operating system in your memory, you're going to use maybe half a megabyte of memory. Okay, so even though gigabytes of memory is available to you, you are only using half a megabyte of it. So that, I mean, what I'm trying to say is that operating systems are very robust in terms of memory usage. You will say this when you take the operating systems and the systems programming course. Okay, so you don't have to, as long as you don't behave too aggressive in terms of using too much memory. Okay, free store is typically large. It should be enough for your typical programs, but it's a good practice to be aware about the limitations. Okay, memory is finite. You don't have infinite amount of memory. It is finite, right? It is finite. So if you are not careful, it is, especially with the recursive stuff, it is easy to finish up your memory and be terminated by the operating system. Okay, it's this delete operator is just the meaning is the same as the free function. Okay, free is a function, delete is an operator. Okay, so this delete operator does whatever the free does. If I have such an example, I have an integer pointer, I have an integer, okay, I have an integer in the heap, its initial value is 5, okay, initialize it with 5. I did something with this new integer, I don't know what I did, and after that I am done, I just deleted this position pointed by P. I am not deleting P. Sometimes I read this as delete P. We are not deleting P. P is an automatic variable, okay? P will be created and deleted by the code produced by the compiler. It is automatic. I don't have to do anything, okay? I don't have to do anything. But this variable that I have created in the heap, I created it myself with this explicit new operator, and I have to delete it, okay? It doesn't have a name. P has a name, right? P has a name. But this variable that is created with new doesn't have a name, okay? So how do I refer to it? I keep its pointer. I say that I know a variable at this address. I know its address. I don't know its name. There is no name for it, okay? I know this address. This address belongs to heap. I am going to use it for some purpose. When I am done, just delete the memory location at that address, okay? Delete that memory location. We are not deleting P. So when you do this, actually, nothing changes with P. The value of P is exactly the same, okay? P is still holding a pointer to that location, okay? That location doesn't belong to me, but P is holding a pointer to that location. That's why some people does this, okay? That's why some people do this. After deleting P, just to make sure that nobody does any harmful stuff with the invalid P, after this one, they just assign null pointer to it, so that I don't try to modify anything using this value of P. As soon as you start doing stuff with P now, which is a null pointer, you get a segmentation fault. It's going to tell you that you're trying to access a invalid area. So instead of a logical error, it's going to be a runtime error. Yes?
Can you ever get access to a new int 5 after the delete P statement?
Can I do where? You mean after the delete statement, do the same thing again?
Yeah. Can you get access to the same variable without the identifier? New int 5.
You are saying that repeat the same thing again here, P new int.
It wouldn't be the same integer, right? Oh.
Well, yesterday when we tried, by coincidence, we get the same integer. Were you here yesterday?
Yes. Oh.
So we did this yesterday. By coincidence, you get the same deleted position again, but it doesn't have to be that way. It may change. Okay? So don't make those kind of assumptions. Don't make those kind of assumptions. Sometimes they may work, okay? It will work on this operating system with this compiler. Next day it may not work for some other part, for some other compiler, or same program might behave differently. So that would be a wrong assumption. Okay? Good. Okay, so the standard terminology says that when you delete a pointer, okay, it deallocates dynamic memory, okay? So literally destroys, I don't know what book means about this, literally destroys memory. There is no destruction done actually, just You just tell the memory management system that I am not using this space, this location anymore. It doesn't belong to me. That doesn't mean that it is destruction. Okay. So that's the delete operator, and this thing dangling pointer is a thing. So if I write the same thing, okay, here, this is my memory. When you say I have a integer pointer, its name is p, so it is in the stack. Okay, let me try to draw this diagram in terms of, okay, remember this is your code, and this is your stack, and this is your heap. Okay, this is your stack, right? Stack. As soon as you say this, at the top of the stack, okay, at the top of the stack, you will have a new variable p, and its name is p again. It's an integer pointer, and I don't know its initial value. I didn't initialize it. But when you say p gets the value of new int, in your heap somewhere, it doesn't have to be at the top, I make a new integer. Its initial value will be 5, and I will put the address here so it points to this location now. Okay, 5 is there. Okay, and when I did stuff here, and when I deleted this, when I delete p, nothing changes actually in this picture. Okay, all I do is, okay, p keeps the same value. If you print, you are going to get the same address, but this address does not belong to me anymore. Okay, after this point, p is a dangling reference. It dangles. Okay, dangling reference. So it is referring to some place that doesn't belong to me, something that you shouldn't be doing. Okay, so dangling reference is a common problem. Dangling reference is a common problem with the pointers, and you should be careful about it. And most of the pointer problems comes from this area, actually, dangling pointers. You don't have this problem with the integers. Okay, there is no invalid value for an integer. When you say integer I, whatever you put in here, okay, if it compiles, then you are fine. There is nothing wrong with using any integer values. But for pointers, some of the areas are dangerous because they are dangling pointer areas. Okay, there are dangling pointer areas, and that would be difficult. That would be a dangerous thing to keep dangling pointers. Keeping a dangling pointer is not a compiler or runtime error. Okay, this p is pointing to somewhere that doesn't belong to me. That's right, but that doesn't mean that I am making a mistake here. I make a mistake as soon as I do this. Cout p. Okay, this is a mistake. This is a bad mistake. Why is it bad? I will not get a compiler error. Okay, my program most of the time will run and print something, and sometimes it will print 5. I don't know. Sometimes it prints garbage. Sometimes it prints 5. That's why it makes it dangerous. So this is a dangling reference. This is not. Okay, this is not dangling reference. This is dangling reference. Okay. So when you say delete p, okay, it gives the memory back to the memory management system. P still points there. Okay, this is the dangling pointer. If p is then dereferenced, when you do this, unpredictable results. Okay, so avoid dangling pointers after delete. You may prefer doing this, just to be safe on the side. This doesn't prevent, of course, dangling pointers, but as soon as you do this, you will get a segmentation fault and your program terminated, and you will realize your mistake. Oh, I forgot about the attendance. Let's start from the, can you pass it backwards? Pass it backwards, okay. so that it finishes here. Okay, so this is the dangling pointer stuff. We talk about this. Okay, dynamic and automatic variables. Yes.
Are dangling pointers and dangling
I'll say it again.
Are the dangling pointers and dangling references same thing?
Yeah. Where did we say? Did we say reference, dangling reference?
You said references a few times.
Well, it is very difficult to get dangling reference. How would you get a dangling reference? I mean, like this. When you say integer reference, this is a compiler error. This is a compiler error because you cannot define a reference without initializing it. Okay, let's say I have initialized it with let's say k is another integer. Okay, afterwards when you say I gets the value of j, it's just an integer assignment. So how would you get a dangling reference? Yeah.
We could define a reference with a freed pointer.
A free pointer. Oh yeah. Yeah, okay. You are saying, yeah, okay, maybe we can do this. You are saying that I have a pointer, and maybe if I do this, I don't know why I'm using red all of a sudden. Let me put, okay. P is an integer pointer. If I do this, then if I delete P, now I is a dangling reference here. Okay, so both of them are dangerous. The other thing is that you return a reference from a function, but you return a reference to a local variable. After the function runs, that local variable will go away, right? Then you have a dangling reference now. Okay, yeah.
For avoiding the dangling reference and pointers, we after delete P, we have to assign P and I a null pointer or just P. After delete P.
Delete P.
No, this part, right part.
Yeah. Well, no.
reference.
Well, this is a dangerous thing. I mean, doing this, yeah, P gets the value of null PTR, will not change the reference of I. I is still a reference to the original P location. So it will stay as a dangling reference. Don't do this. I mean, this is not a very common code. Common dangling references comes from the function returns. Okay, you are returning this like this. I am returning an integer reference from a function, and I have an integer and return an integer. So what did I do? I return a reference to a local variable, right? And local variable, so it seems nice, but can I do this? Of course I could do this. Function f gets the value of 7. Can I write this? Of course I could, but there is a dangling reference here, right? Why? Because f returns something that is going to be killed as soon as f runs, okay? And I am trying to assign something to it, and this will work, this will compile. Most of the time it will make an assignment. Sometimes it will crash, but anytime you run this, you are running something faulty, something bad. So this is called dangling reference. Dangling references are less common than dangling pointers, but both of them are bad things. Okay. Good. Any other questions? Good. So let's talk about this dynamic and automatic variables. Okay, dynamic and automatic variables. Any variable, integer f, character c, double d, dot, if something happens okay, make a new integer k and money end of if and return 7. Okay, this is a local variable, it's a parameter. Local variable, local variable, local variable. Okay, these are local variables and these are automatic. Okay, you just say that I need this type variable and I'm going to give you a name to it. Okay, these will be created as soon as you declare them, and they will be killed automatically when you are done with them. Okay, character C and double D will be killed here. Integer k and money m will be killed here, right? So these are automatic variables. Okay, you declare them, they have a scope, and they are killed automatically. That's why we like them. Okay, because we don't have to think about when they are going to die and when should I kill them, and etc. Dynamic variables are different. You have to create them using new operator. Okay, once you have created them, you have to destroy them somewhere in your program, and they are not local. Okay, once you create them, they will continue living. Okay, let's look at this one. For example, if you do integer pointer pt gets a new integer here. Okay, pt is a local variable, it is automatic, it will die here, but the integer that you have that you made on the heap with the dynamic memory allocation here will continue living after even this function ends. Okay, so who is going to kill this variable then? Since you created it, you have to kill it. Okay, otherwise, I mean, this is a very bad code, because every time I make a function called f, it will make a new integer on the heap and nobody deletes it. So I am losing the address. Nobody remembers the address, right? Who remembers the address? PT. PT will be killed here. So I keep making a new integer on my heap every time I make a function call. Okay, and it will stay on the heap. Nobody is going to use it. Nobody will be able to use it because nobody knows its name or the address. So every time I make a function called f, I am losing some memory. What do we call this error? This is called what?
Memory leak.
Yeah, memory leak. We are leaking memory. So this is a very dangerous loop for f. It seems like it's a infinite loop. It will run infinitely, because I am not doing anything in it. I am making local variables, doing some stuff, I'm returning it, I'm calling it again and again. No, every time I make a call, I am losing 4 bytes on my heap, right? So my memory is finite. After some point, there won't be any space on my heap, and the operating system will terminate my program and will tell me that I have terminated this program, it was using too much memory. Okay, one of those new statements will fail. It will return a null pointer, or the newer compilers, it will be terminated. Okay, so local variables and automatic variables are two types of variables, and we like automatic variables. If you can always use automatic variables, they are less troublesome, but dynamic variables has this nice property of you can specify the size of it, you can change the size of it, make it small, make it large, and also how long it's going to live depends on you. Okay, how long it's going to live depends on you. Okay, so automatic and dynamic. Dynamic variables created with the new operator, created and destroyed while program runs. That's what you're going to do. Okay, local variables declared within function definitions. They are either your parameters or your local variables, block variables. They are not dynamic, and they are created on the stack. dynamic heap, okay, local variables stack. Okay, good. How about the globals? Are globals local or are globals automatic or dynamic? Yeah.
Automatic.
They look like automatic because we give them names, but they are created as soon as my program starts running, and they end when my programs end. It looks like, it looks like they don't need the stack. They can be on the heap. So they are kind of in between because they don't have a scope. Their scope is the whole program after the declaration, right? They are kind of in between, but you don't have to kill global variables, and they have their names. But the other thing is that they don't die. They don't die before your program ends, right? They keep living until your program ends. Okay, your dynamic variables are the same. They keep living until your program ends or until you deleted them. You don't have a question? Okay, you're just yawning. Okay. Yes.
Is there any way to delete a variable in this stack?
Is there any way to delete a variable?
In this stack?
No. You can't do this. But syntax-wise, it seems okay. Your question is, can I delete this? Can I delete this D?
Yes.
Yeah, well, this is double D and you can double pointer. This will compile, and this will probably will be ignored. I don't know. Well, definitely, this is an evil thing. Don't do this, but try it. Okay. See if it is going to give you a runtime error. It will, because stack doesn't belong to heap. A memory management system only manages the heap, not stack. Okay. You cannot put holes inside stack. What is the meaning of stack? Okay. Tell me the meaning of the stack. Last in, first out, right? Last in, first out. Or using the first letters. Like for. Okay? Last in, first out. Whatever you put at the top, it will be the first to get out, okay? You cannot change the order. You don't say, I am going to remove the double in between the stack. No, you can't do that, okay? You either push to the stack at the top or you pop from the top. Okay? So that's how the stack works. You don't delete, okay? You don't delete anything from your stack. Okay, you are not allowed. Even if you are allowed, it would be a bad thing because that's just against the idea of using a stack. Stacks are very simple, but as you are going to see next semester in the data structures course, they are very, very powerful. They are very, very powerful to be used in many complex problems. Okay. Without the stacks, we cannot do. Without the stacks, we can't do any, for example, function calls. We do it with the help of the stack, or the local variables, we do it with the help of the stacks. Recursion, definitely, without the stacks, there is no recursion. Okay? Good. Some languages didn't use any stacks at all. It was, for example, Fortran, the original version of Fortran didn't use the stacks, but it was very limiting. It was a very limiting thing. So we talked about the dynamic and automatic variables. Okay. Well, some people say that I am confused about the pointers. Okay, when I see this, I got confused. Why don't I define a new type definition? Okay, type def integer star int pointer. So int pointer becomes a name for this type, integer pointer. After that, I would say integer pointer p, like that. Okay, so they say that this is less confusing. I don't know. For me, this is more confusing. I have to remember what int ptr is, right? but this is sometimes preferred. That's what the book says, that's why I'm talking about it. Okay. Call by value by pointers. Of course, like this is a call by value over integer, right? Call by value over integer, and this is a call by value. Let me make it a different name. Call by value over a pointer, integer pointer. Both of them are call by value. Okay. One of them is accepting an integer value. The other one is accepting a integer address value. Okay. So whatever is passed, this one makes an integer copy. This one makes a integer pointer copy. Of course, within G, okay, I can dereference this pointer and change the value of that location. So that would look like I am doing call by reference over the value of the reference P. But it looks that way, so that's why we say it is simulated. But in fact, what you are doing is call by value over integer pointer, and this one is call by value over I. Okay, thank you. Did everybody sign this? Everybody? Okay, so and I think this is, yeah, just for the sake of example, and say that, okay, I'm going to define this integer pointer as int pointer type def. Okay, this is not a new type. Okay, it's a new name for this type integer pointer. It's not a new type. Okay, and there is a function, it calls an integer pointer, but it's int pointer temp, and it calls it sneaky. Well, it is not that sneaky actually, because it takes an integer pointer, but the book calls it sneaky. So here I have an integer pointer P. Of course I can do this, new integer assigned to P, and that reference P is 77. When I run this, it will say print 77 on the screen, right? 77 will be printed on the screen, and I will call sneaky P. What does sneaky P do? Okay, sneaky P takes this integer pointer, at that reference it changes value to 99. Okay, after line 16, my value of okay, the reference P will be 99, not 77. And after that I will print it, it will print 99 on the screen. Okay, so that's what it calls as sneaky. But this is no different than calling a function with a call by reference. Okay, with the call by reference, you send a variable and its value changes, and this kind of the same thing. And of course, this guy forgot to delete P, right? Why did they forget to delete P? Because your memory will be given to the operating system anyway after your program terminates. Operating systems are again smart enough nowadays to claim back all the memory used by a program. Okay, previously when the operating systems were weak, okay, they weren't very powerful, they didn't know much. When a program terminates without deleting all those memory, it is gone. Okay, the operating system wouldn't know that that program did not delete some of the heap place, and every time you run that program, it keeps stealing some part of the operating system's memory, and after a while the whole system crashes. Nowadays I don't have that situation. I mean, no matter how bad I write my program, usually it is very difficult to crash an operating system. Okay, well, it is easy to crash your program. All you are going to do is just try to write to some dangling reference place, especially null pointer, that will crash your program. But crashing an operating system is difficult. It is very, very safely protected from the user programs. Well, of course, I am not saying that it is not possible. It is possible from time to time. I think my computer crashes every week, every other week, I don't know. But previously, it used to be your program, your operating system crashes 4 or 5 times a day, if you are not doing any fancy C programming. If you are doing some fancy C programming, your operating system crashes maybe 5 times, 10 times an hour. Every time you make a mistake with your C program, your whole operating system crashes because there was no protection. Because the computers were weak, operating systems were not that powerful. Nowadays we don't have that case. Good. Okay. So we talked about this. I am going to skip this part. Okay, let's talk about arrays. Okay. Arrays are actually okay when you declare an array, okay, when you say I have a money array of size 100. Okay, you could say that, right? So 100 money objects will be created. Where is the living address of this MAD array? Is it stack or is it heap? Guess again. Stack. Okay. It is stack. Why should it be heap? What is the rule for creating a variable in heap? New operator. Did I use a new operator here? No. This whole array lives in the stack. Okay, it's a automatic. Okay, so if this is my block beginning, if this is the beginning of the block, okay, this is the end of the block, your whole array will be killed here. Okay, all 100 of them will be killed here automatically. You don't delete them. Okay, this is not a dynamic array. This is just a regular array. It is created on the stack. Okay, when I do this, there will be, okay, let's say this is my program code. This is my stack. On top of my stack, there will be 100 money objects. Okay, and MA is a pointer. Okay, the type of MA is something like this. The type of MA is money MA. Okay, so what does that mean, money MA? It's a pointer to a money object, and it points to at the beginning of the money array. But the thing is that it's a constant pointer. It is not. It is something like this. Okay, const MA. Okay, so MA is a constant. You cannot change it. It's a money pointer, and it points to its location. Okay, so it is okay to say I have a money pointer. Come on. I have a money pointer MP, guess the value of MA. You could write that, right? Why? Because MP is a money pointer, MA is a money pointer, I can assign it. But you can't do that. You can't say I am going to assign a null pointer to this MA. Why? Because MA is a constant. Okay, so this is bad. This will not compile. This is good, and this will compile, and sometimes we do that. Okay, so arrays are actually basically pointers, and that's it. When you declare an array like this, an automatic array, it's a pointer. Okay, it's a pointer. It's a constant pointer. You can't change its value, and using this pointer, you can do anything allowable with pointers, and we are going to see a few examples in a few minutes. Okay, any questions up to now? Any questions? Let's take 15 minutes of break. Let's be here around 10:33. Alamazsın, sordum ya. Sormadın mı ben de bunu imzalamayan var mı diye?
Hocam ben baktım da iki kez yoktum, sonra gittim o kontrol ettim telefondan. Telefonum kapalıydı. O yüzden biraz geç kaldım.
Hocam bu arada
Geç geldin de ben dersin
Hayır,
sorun
geç
da al.
gelmedim, geç gelmedim. Yani size sormaya geç kaldım.
Nerede ismin?
Arkada olması lazım. Şu 44, ha, şurası yazmıyor hocam.
orası
45,
yazmamış,
aynen,
biz de
o
bu
yüzden.
şekilde yazdık.
Orası
41'den
yazmıyor mu?
sonrası çıkarılmamış.
Ben
Allah
de
Allah.
kendim görmedim, 44
Sadece
hocam.
40 kişi almıyor mu bunu?
45.
Orada var, burada yok ha.
Evet.
Hı hı.
Garip.
Ben
Tamam.
hocam boş yere imzalamıştım. Ben bir tıktım varken.
Sen de değiştir onu. Niye öyle ki acaba? Siz soru mu soruyordunuz?
Bunu söylemişim.
Tamam.
Hocam ben şimdi geldim de raporum da var. İmza atabilir miyim?
Raporun varsa raporunu göstersin eğer kalırsan. Bana gösterme, hayır. Sen geç derse, eğer devamsızlıktan kalırsan de ki benim o gün raporum vardı, bir ders daha ekleyeyim buraya, tamam mı?
İmza
Raporun varsa
atayım.
niye geldin iyi sen?
Ben kan verdim de yani
Ha,
Teşekkür ederim.
derse
Hocam ben de şuraya imza attım ama kalsın mı burada?
kalsın tamam.
atmayayım değil mi imza şimdi?
Yok, atmayın. Sana attırırsan birileri onu bana hatırlatır. Hocam onu attırmıştın da bilmem ne de falan.
milletin şeyleri gibi o kadar rahatsız oluyor.
Ya ama şey bak ya Gebze'nin internet sorunuyla ilgili yorum yap. Adam makamada düşmüş yapacak mı?
Kanka şimdi
Mail atmıştır.
beyler izle. Çağırayım mı? Direkt böyle bir derleyelim.
Yani elimizden kalmamış. Önce oğlum sen iyi yaptın ama.
Ne fark etti ya oğlum?
Bir kodu aç bir. Niye veriyorum?
Lokal belediyenin adresinden adres kullanımlar. Ama bu direkt olarak
Tamam da
yaşatıyoruz.
buradayken yapılmıyor. Ben dediğim gibi.
Tam buradayken yapalım mı? Return de verir. Tamam onun zaten niye yok? Öyle bir sorun yok.
Error'u verdi mi onu?
Tamam.
Tam error vermedi işte.
Bakalım bir daha yapalım.
Tamam sana yere ben artık çıktım.
Runtime de mi hata veriyor? Oğlum öyle bir demedin ki bana.
Öyle mi? Okey bu arada. Monitörün şu. Sıra çekmedi. Yapılacak diye var. Hanımefendi de şahsen bana vermeyebilir bu arada. Efendim? Oldu mu? Sadece blok kaydı. Peki öyle şey.
Ya olsun mu o kadar?
Bulanık görüyorsun değil mi sen de? Dedim acaba evet gözüm yine bulanık gördüm. Dedim acaba benden işte.
Sen hiç monitörler nasıl blok yazdığını
Hepsinden
Postfix'e şey prefiksi şunu yaptım da hangisini yaptım hatırlamıyorum.
So dynamic arrays, is this is a static array. You cannot say that now I will need k number of money objects. I am going to change its size and increase it and make it larger and etc. For that you need to use dynamic arrays. And dynamic arrays means that you need to create your array on the heap. Okay. So standard array is fixed size. This is standard array. Okay. With the dynamic array, size not specified at programming time and determined during the program running. So it would be something like this. It would be something like this. Now I have a money pointer dynamic array. You will say I need an array of money objects and I need k of them. K is an integer, for example. I don't know what it is. It is calculated somewhere. Okay, so I need this one. Once I use it, I don't know what I use it for. Doesn't matter. Somewhere in your program, you have to delete this money array. And the arrays are deleted this way. You say delete DA. Yeah, that's true. So DA is pointing to a money object. I know that because DA is a money pointer, right? But the compiler doesn't know that it needs to delete an array because there is not a single money object in there, okay? So you need to tell the compiler that DA is pointing to an array. So delete all of them. Not just one, but all of them, okay? So if you just say delete DA, it will try to delete only the first one, okay? But if you do this, it will delete the whole array. It will know that DA is pointing to an array and it will delete the whole array. Okay, so this is a special notation for delete. It is used for deleting arrays, and also this is a special notation for making arrays dynamically on the heap. Okay, this array here, okay, this array MA is a static array. It is created on the stack and it will be deleted at this point, okay, when this scope and this block ends. But this array will be deleted when you delete it. If you don't delete it, it will not be deleted. Okay, so you need to be careful about that. And if I forget about this line, after this block ends, this will be gone, MA will be gone, MP will be gone, right? And what else? K will be gone, DA will be gone. They are local variables, but this array will be kept in the memory. It will not die unless you say something like that. Yeah.
Can we say delete 5DA?
No. The question is, can we say delete 5DA? I like to delete just 5 elements of it. No, you can't. Okay. The size is known by the memory management system, and it deletes the whole array. Well, actually, when we talk about the destructors, what I'm saying is not exactly correct. the array is deleted, but when you do this this parentheses thing, there is special something else going on, and we'll talk about it today. Yeah. Any other questions? Yes.
How does get delete know the size of DA?
Well, it's a detail of the memory management system. Okay.
My question is, if that whole thing is a function and I return a pointer
Yeah.
that exactly same as the DA.
I know what you're saying. You are saying that I am contradicting with what I said before. I said that arrays are just simply pointers. When you pass them to a function, you need to pass the size, etc. Right? That's what you are saying. Again, I mean, how would the memory management system know that DA is pointing to an array and its size, right? So, well, I mean, memory management system is more complicated than what we are thinking. I mean, when you say, give me an integer, 4 bytes of integer on the heap, it has to record that information somewhere. It keeps a table of what is allocated, and it knows its sizes. Okay, how many of them are there, and etc. So when you say delete array DA, you are kind of basically telling the memory management system that you make a lookup in that table, find that position, and that there has to be an array, and find the number from there. Okay, so I mean these are all hidden from us. All we do is we create arrays and we delete them. We create them using this notation. We delete them using this notation. Okay. So that's a detail of memory management system. I don't know how it really works. I'm just guessing. So it has to keep that information. I mean, when you are deleting a single money or when you are deleting a single integer, you know the size of it, right? It knows it automatically. It's single money. But when there is a array, so that information has to be kept somewhere. Yes. Yes.
Can I delete an index operator just single pointer, or it has to be an array? For example, I have a pointer and I say to user, you can use this array or just one single element. How can I
I think he asked the same question. Can I delete some part of this array? No. You have to delete the whole array.
No, not just some part of, not some part of. I don't know it's an array or just single pointer. It depends on user wants.
You have to know it. I mean, when you are deleting something, you need to know if you are deleting an array or a single object. It is your responsibility as a programmer. Okay? If you're asking this, I mean, how would I know what I am deleting? It is your responsibility. Okay? So, there is no other way of using this actually. You just make an array like this and delete it like that. There is no parameters involved. There is no... by the way, this is just a regular pointer. I mean, the compiler doesn't know that DA points to an array. DA is just a money pointer, that's it. Okay? So what did we say? This MA is a pointer. Well, it's a constant pointer, but it's not anything more than a pointer. It's a pointer. So you cannot change its value. Here you can change its value. It's a non-const pointer, and it is pointing to a money array, but it didn't have to. Okay, let's move on with the examples, and it will be clearer now. Okay, so an integer here this is a local two things. This is again my program. Here is the code section. This is my stack. This is the top of the stack. This is my stack pointer. When you say 10 integers, okay, 10 integers at the top of the stack, I will put 10 integers here, and after that there will be a pointer p. Okay, this is a and this is p. Okay, that's how the memory looks. Okay, So A and P are both pointer variables. Okay. P points to somewhere. Actually the name A doesn't have a place in the memory. I mean, P has a position, right? P can point to anywhere it likes. You can change it. A is a constant. It doesn't. I think somebody asked me this question at the beginning of the semester. I wonder where the number 7 lives in the memory. That was a very good question, actually. Where is 7? Do we have an address for 7? No. 7 doesn't have an address in the memory. We don't store it, okay? It's a constant, okay? When you do this kind of stuff, 7 times 2, these two are used for a calculation, okay? CPU handles and it gives back the result, okay? You don't keep 7 and 2 somewhere special in the memory. They don't have addresses because we don't change them. Again, A doesn't have the name A doesn't have a position in the memory, but its value is this position. Okay, it's a constant value, and that constant value is this position here. That's why we kind of show A like that. Okay, so for the constants, you don't have any positions in the memory while the program runs. Okay, we talked about this, and I can do, okay, this is perfectly legal. Why? Because P is a pointer, integer pointer. This is a constant. Of course I can do this assignment from constant to non-constant, but this is illegal. I can't assign a value to a const pointer. Okay, A is a const pointer. You can't change its value. Okay, you can't say A plus plus. Of course you could say P plus plus. This is okay, but A plus plus is not legal. You cannot modify its value. You can take it, you can copy it, but you cannot modify it. Saying this is very similar to saying 7 plus plus. Did you try it? 7 plus plus and plus plus 7 is the same thing, okay? Because, I mean, you need to modify the parameter of it. You can't do that actually, so this is bad. This is, I mean, these two are almost the same thing. Those both of them are bad stuff. Okay, we talked about this, and when you say int a10, it's a more than a pointer variable. It is integer star const type. Remember that? A is an integer star const. So what is this? Okay, let me write this again. Okay, maybe you did this before, but we have integer star, we have constant integer star, we have constant, we have integer star constant, and we have constant integer star constant. Okay, 4 different variables: p1, p2, p3, p4. Okay, I write them without my glasses. Let me see what I wrote. Yeah, these are, they look, I can't read them, but okay, yeah. Maybe you like it better. Okay, so let's see what we can do. Let's see what we can do. How am I gonna do that? Okay. What can I do with a pointer? I can increment the pointer, right? P plus plus. I can dereference it and assign a value to it, or I can do C out. What is D? It says to be okay. C out P. What kind of other things do you think I can do? Okay, let me make a table like this. Well, addition and yeah, okay, so maybe you are saying that P gets the value of P plus 2 maybe. Okay, so I'm going to do this. 1, 2, 3, 4. If my pointer is P1, can I do P plus plus? Yes. Can I do this assignment? Dereference P gets the value of 2?
Yes.
Yeah. How about this? C out dereference P? Of course and of course. Yeah. So for P1 I can do whatever I want. How about P2? Can I do P plus plus with P2?
Yes.
No.
Yes, no?
Yes.
Yes. This one doesn't say that P2 is constant. It says that whatever I am pointing to with P2 is constant, right? So I can change its value, but I can't do that, right? I can't do that. Also, of course, using this, I can dereference it, and I can change, of course, value. Okay, how about 3? It says that integer star constant P3. Can I change the value of P? No. I can't. But, of course, I could do this and this because it doesn't say that I cannot dereference. I am just dereferencing it, and I am just change it or not change it. How about P4? Is it going to be all reds?
No.
Of course not. If it's going to be all reds, then why am I using such a thing? This will not happen. This will not happen. This will not happen, but this can happen. Right? Okay, so what is this? This one is number int A10. This one is number this one is number what? Number 3, yeah. This one is P3. How about this one? Const integer B10. How about this one? What is this? This is number 4, right? You cannot change B. Also, you cannot change anything inside that array either. Okay? So it is number 5. So this is P4. Okay? Try all of these. See what kind of error messages you are getting. Okay? I mean, trying to understand the error message itself. Why did they give me this error message? What do they mean? I mean, I know the error. I know what the error is, but the important thing here is that trying to understand that error. Why I am getting that error, that specific error. Okay, so we are looking at this P3 and P4. Any questions? Yes.
You need to initialize the array constant P10.
You mean this one?
Yes.
Yeah. Without initializing it, then you have a bunch of uninitialized. Yeah, you have to initialize this when you are doing it the constant. Any constants that you define anywhere, you have to initialize them, of course. I didn't initialize them in this case. Yes?
Where can we use these P4?
Where can we use this P4?
Because we couldn't change anything.
Well, this is P4, right?
Yes, but why can we use it?
Well, let's say you have an array of colors, right? On a computer. You have 16 colors available, and my first color is red, then green, then blue, then yellow, etc. I know that I cannot add new colors, or I can't remove any colors because these are the colors that are supported by the hardware. I can't do anything. So I keep them in a in an array, right? Or in your case, in your homework, if you like to keep the state of a cell could hold it could be an empty, it could hold a peg, or it could be an invalid cell, right? So array of 3. So these are kind of the enumerations of, yeah, your enumerations are kind of constant arrays, right? So there could be those kind of cases.
So we have to initialize.
Or the number of days in a month, okay? January is 31st, then February is 28, then 30, 31, 30, etc. So these are constants, they don't change. 12 elements, and I have 12 elements and their values are fixed, and I promise I will not change them. Okay? Good, okay. Let's move on then. Let's move on. Dynamic arrays again. Array limitations, the static array limitations or the stack array limitations must specify size first. As I said many times before, you don't write this. You cannot say integer a k. No, don't do that. Okay, you always have to say integer a 100 or some constant number here. K cannot be a variable. Okay, must specify size first. Okay, must specify size first. So what if I don't know the number 100 here? Okay, I don't know what kind of size I am going to have. So you can't use the static arrays in that case. You can't use the static arrays. You can't use the stack-based arrays. You have to use the dynamic arrays, which is the arrays that are created using the new keyword. Sometimes you might say that I don't know the value of k, but it could be at most 100. So I am going to declare something at 100. So I am not going to use most of it. So that's kind of a waste of memory. We don't want to do that. So it's going to be dynamic arrays. It can grow and shrink as needed. We are going to do that. Okay, dynamic array is very simple. Use the new operator. This is what you do. Okay, I have new double 10 and d creates a dynamic array. Okay, when you delete a dynamic array, of course you have to do this. Deallocates the memory. Okay, the brackets indicate array is there. Okay, so d still points there. So maybe after that, maybe you should say d null pointer. Good. We already did that. Functions, of course, can return arrays. An array means that actually it's a pointer. You just return a pointer. So don't do this. This is bad syntax error. Yes?
Where does variable sized arrays fit in?
Where?
Variable sized arrays.
Where is it useful?
No, where does it fit in? What is it, dynamic array or?
Yeah, of course it's a dynamic array. Okay. Dynamic array means that it is creating using a new keyword.
No, I was saying, where does the variable sized arrays fit in the context of arrays?
I don't understand your question. There are two types of arrays, the book says. One is the static arrays, which are stored on the stack. The other one is the dynamic arrays, which are kept on the heap. Okay, there are two types of it. Your question is, where does the idea of dynamic array fits in?
No, variable sized arrays. Variable size.
Variable size array. What do you mean, variable size array?
I know there was such concept in C.
Well, dynamic means it's variable, right? Dynamic array is a variable size array. Is that what you're asking?
Yeah, I guess so.
Okay. Dynamic means it is not static. It is variable size. So whatever you do with malloc, you do it with the new now. Okay. So pointer arithmetic is again still valid in C++ like we did in the case of C. When I do this operation, let's draw the memory again. Okay, this is my program again, and this is my stack. At the top I have my heap. Okay, this is heap. When I say new double D, okay, of course D is a local variable at the top of the stack, and when I say new double 10, there will be 10 integer allocation here. Okay, there are 10 integers now, and D is pointing to the beginning of this 10 integers. Okay, so D is a constant pointer. You cannot change the value of D, but of course you can just add 1 to it. When you add 1 to it, okay, so there are again 8 elements in it. I'm trying to draw it like that. Okay, D is pointing to here, so this is where D points to. D, let me, okay, D points to here. D plus 1 points to just the second element of the array. This is the first element at the top, this is the second element, and this one is D plus 9. This is the last element of the array. Okay, so the plus operator with the arrays, with the pointers, of course they work. Okay, plus 1 means that give me the next double after this D. So D plus 1 actually, in actuality, if you are doing with the byte calculation, adds 8 bytes to the value of D, because the size of double is 8. And this one will add 9 times 72 to the value of D to get this position. Okay, so these are, of course, this is a pointer, and this is a pointer, and this is a pointer. They all point to different places. And of course, when you say go to this position D plus 9 and dereference it, now I'm going to assign 2.17 there. It will write 2.17. Oh, what is semicolon? Okay, at this position. Pointer, I am dereferencing it. So this is called array arithmetic, or pointer arithmetic. Plus operator, the meaning of plus operator works with this way. Remember what I said, the meaning of plus is different for integers or doubles, and the meaning of plus is different for the pointers. I have never seen such case like D is a P1 is a pointer plus P2 is a pointer. I have never seen an example of this. Nothing good will come out of this one. Okay, what we do is usually P1 plus some integer, some integer K. Okay, so this is okay. I am not sure even this will compile. It might compile, I don't know. Even if it compiles, nothing good will come out of it. It's a bad line. We write it this way: add some integer to P1. What is the meaning of it? Give me a new pointer. The new pointer will point to P1 plus K times size of whatever the pointing value of P1 is. If P1 is a double pointer, it is K times 8. Okay, so it will be incremented. If P1 is a money pointer, it will be K times size of money, whatever it is, in terms of bytes. Okay, good. Any questions so far? So that's the pointer arithmetic. I think maybe I should show you. Maybe I think show you one of the examples from the book. Is this one good? This is just stupid indexing stuff. I am going to, okay. How about this one? No, we know we can do better than, yeah. Now this one is interesting. Let's look at this one. I have an integer a. Well, it is not that interesting, but it kind of makes me, it makes it easy for me to talk about some stuff. I have an integer array A initialized with 5 values and a pointer B, integer pointer. And then I have a function named double. Doubler takes, as you see, it takes an integer pointer and a size of the array actually. So we are going to say A comma 5. And let's see what doubler does actually. Here it is. It takes an integer array, integer pointer, and the size. Look at what it does. It says that I am going to make a new temporary integer array, and I am going to initialize that array with the values of 2 times the value of AI, like this one. See here. I am going to do this, and I will return this as an integer pointer, which is okay. So when this function is done, okay, okay, this size will be gone because it's a parameter. Integer pointer A will be gone. Okay, this temp will be gone. I will be gone. Yeah, I know that. But the array that I have created will stay in the heap because I did not delete it, right? So I returned it. Whoever guessed this, okay, it assigns it to a new variable B. So B is another array of size 5, and it contains the values of 2, 4, 6, 8, and 10. Let me put it in here, and let me go back and try to make it like this. Where is okay, I'm trying to draw the shape of the memory now. Again, I have this one. I will draw it like this. This is my program. This is my stack. This is my heap. When I do this, A is an array. Of course, at the top of my stack, I have my array A, and I will put these values 1, 2, 3, 4, 5. Okay, this is my array A, and this one is in stack. Okay, this one is in the stack. When I call this function doubler says that, okay, I have a new parameter. Okay, let's put the parameters. Parameter A, size, okay, temp, and I. These are all put on top of the stack. Now this is my stack pointer. Okay, so my array A lives under these, and I put all of my temporaries here. But after that, it says that, let's say this is my heap. Okay, and this is the empty area. Inside my heap, I create a new array of size 5. So let's say this is my new place. And that place, okay, that place will include values 2, 4, is that correct? 2, 4? Yeah. 2, 4, 6, 8, and 10. Okay, so this temp is pointing to this place. Okay, so when this function ends, all of this stuff will go away. Okay, this function ended, and all of this stuff will go away because those are automatic. So my stack kind of shrank. And when I come back here, I assign the return value to B. By the way, B is a local variable here. B is a local variable. Where does the B point to now? After line 15? It points to this location now, because I return I return the pointer to that location here. Okay, it points to that location, and now this is the case. So B is pointing to some place in the memory. It is in the heap. All of the stuff that comes from the double are gone. All I have is just two variables, okay, two local variables, A and B. A is an array, B is a integer pointer, and go this way, okay? So when I say I have a new integer I will be allocated at this position, okay? So it says that print all of the values of I. This one, AI, it will print 1, 2, 3, 4, 5. But this one will print 2, 4, 6, 8, 10. Okay? And at the end, I say I am deleting B. When I say I delete B, okay, this position will be returned to the memory management system. And at the end, here, A and B and I will be deallocated automatically. So the one that I have created here, okay, the one that I have created here, here will be deleted there, okay. So this function is not a very nice function because it is returning a dynamically allocated array, and you are responsible as a caller, you are responsible for deleting the returned array after you are done with it. Okay, it's like malloc. Okay, malloc returns you something, you use it, but when you are done, you need to free it. You have to. You don't forget. If you forget, you have memory leak. This is kind of the same thing. Okay, it returns you an array, and you are responsible from deleting the returned array. Okay, these kind of functions kind of create trouble because you have to keep it in your mind, and sometimes you forget about deleting them. Okay, so this is that example. I showed you this one. How about 10.9? Let's look at 10.9. Okay, so this 10.9 is about two-dimensional arrays. Yeah, let's look at this one. Okay. It says I have two variables, D1 and D2. Give me the two-dimensional array sizes. Okay, the number of columns and number of rows. Here they are, D1 and D2. And look at this one. This one says that I am going to create an array of type integer pointer. Okay, remember this int array pointer is an integer pointer. So M is not an array of integers, okay? M is an array of integer pointers. Okay? M is an array of integer pointers of size D1. Since D1 is not a constant, I have to make this a dynamic array using the new operator. Okay? So it looks like I am going to do this. I am going to do something like this. It will be like this one. There are D1 number of rows, and there will be D2 number of columns. Like a matrix, right? Two-dimensional array. D1 number of rows. So each row is like an array, right? Each row is like an array. So D1 is the number of rows or the number of arrays. So where do I keep these arrays? Okay, where do I keep these arrays? I will keep them okay, inside this array M. M is an array of integer pointers. Each integer pointer is an array, right? Is an array of integers. And then with this loop, I iterate over the elements of this M, iterate the elements of this M, make it a little bit bigger for you, okay? And every time I make a new integer array. So things got a little bit different now. So the picture that I had drawn doesn't reflect this anymore. So the picture that I had drawn before it was something like this. So it's like a regular matrix kind of a thing. No, it is not actually. Here is the thing. What was M? M is an array. Let's do this in memory again.